the starting point. Example number 4. First, let's look at our question. Log. Here, look at the log. Log of n belongs to little o of n. We know the meaning of little o. Take the ratio of two functions, then calculate the limit. And when n goes to infinity. Okay, all right. Here, remember, in our typical function, n is discrete variable. Remember the last time I talked about discrete variable and continuous variable when we calculate the limit. The reason why we need to consider discrete variable and the continuous variable, because there is a big method called the L'Hopital's rule, using derivatives to do the limit calculation. But if you want to calculate the derivatives, you have to use the continuous variable. All right. So here, let me switch to, here at the beginning, I plan to apply L'Hopital's rule. L'Hopital's rule, indeterminate form. First check. The ratio must be an indeterminate form. Infinity over infinity, indeterminate form. That's correct. So we can go to the next step. Here, remember, we replace n by x. After this replacement, we know now we have a continuous function, x continuous variable, so we can consider derivatives. So that's the reason we use continuous variable. All right? Here, let me talk about some comment at this point. If you read our textbook, in this situation, the textbook does not use the rigorous math. Okay? The textbook still uses the discrete variable and taking derivative for discrete variable. That's not rigorous. Okay? So that's some problem in the textbook. Okay? We want to do the rigorous math, so we change here. We use the continuous variable here. All right. And we know when we use the log of n, the hidden base, we assume a greater than 1 hidden base. There is some constant, a greater than 1 as the hidden base. Okay? All right. So later, so you will not have question. I couldn't find the base number. That's the hidden one there. Now, L'Hopital's rule, numerator derivative, denominator derivative, denominator very easy, just 1. The numerator, you need to find the formula. Okay? 1 over that denominator, the base, natural log of that base, That's the reason we need a greater than 1. In that assumption, natural log of a is a positive number times x, the variable x. All right. After simplification, after simplification, we have this expression, 1 over constant times x. Now when x goes to infinity, it equals 0. Try to follow. If you have the background knowledge, the derivative you can find either from web or from some calculus book. Okay? So you need to find somewhere if you cannot memorize. Most of you probably cannot memorize derivative formula, but just find it. Okay? All right. After that, then by the definition of little o, limit definition of o, yeah, we have the conclusion. Yeah. So that's example number 4 for this part. Yeah. Yeah. If you have a question, just let me know. Yeah. All right. Next example, example number 5, this time a little harder. Power function, n to the d. What is the d? Some unknown constant, positive. Little o exponential function, a to the nth, a d greater or equal to 1. Yeah. Yeah, here a greater or equal to 1, but yeah, but later we will see. If later we only require d constant. Yeah. In this example, we assume it is greater or equal to 1. This example, only this example. Yeah. A greater than 1. Yeah. All right. And in this example, we use d as integer. So that's why we make it greater, positive integer, greater or equal to 1. Yeah. Later, we will change it to a real number, positive real number. We don't require integer, but in our first power function example, we want to make it a little easier, so we make this integer assumption. Later, we will relax that restriction, make it more general. Yeah. All right. Ratio of the two functions, limit, and L'Hopital's rule. In order to apply the L'Hopital's rule, we need to use the continuous variable x. Okay? Yes. To make our thinking more rigorous. Make our thinking more rigorous. We're not satisfied with just get a correct answer. Yeah. If you use the textbook way, still using n there, taking derivatives, although you can get a correct answer, but your thinking is not that rigorous. So that's not a good training. Yeah. So I like to give you, solid logic thinking training. Yeah. So that's why I want to put a rigorous math here. Yeah. All right. Then we can safely apply L'Hopital's rule here. Power rule, remember, derivative of x to the dth power, we apply the power rule, the formula for the power rule, and derivative of exponential function, that's the formula. After simplification, let's do simplification. Yeah. So we have a lot of constant thing, part. Yeah. So then remaining functions after simplification, you can see, similar the format as the original. You apply another L'Hopital's rule here the second time. Okay? Second time. Each time you bring down the exponent by 1 based on the power rule. Second time you bring down the exponent number by 2 and so on. All right. Look at after d times, you apply L'Hopital's rule d times. So the constant d factorial, the denominator natural log of n d times, dth power. Yeah. X, the power term, bring down d times d minus d, 0. It's gone, right? X to the 0th power, that's 1. So after simplification, you have d factorial over parenthesis natural log of a to the dth power, then our original exponential function, x, a to the xth exponential function. Yeah, when x goes to infinity, it equals 0. Yeah, So that's why it is hard, because we apply L'Hopital's rule d times, and get the answer. All right. Yeah. Try to follow this procedure. Yeah. You need math knowledge to go through. Yeah. You need to do the simplification right? Yeah. And finally, you get to this point. Then, by definition of little o, we have that conclusion. Yeah. And we can, after this step 0, then we can go back to m. We change continuous variable back to discrete variable. Why we can make the change, I explained the last time, right? So when you have a limit when n goes to infinity, you have a limit already. Yeah. How to go to that limit? Then you have the freedom to choose how to go to the limit, right? Yeah. Because here we only require x goes to the infinity. We do not specify which way to go to infinity. All right? We have freedom to choose which way to go to infinity. How about you just choose the discrete value to go to infinity? Right? 1, 2, 3, 4, discrete value to go to infinity. So you're fine. You do not violate any rule here. Yeah. So that's why after you get this limit equal to 0, you can replace x back to discrete variable n without any problem. No violation at all. It is rigorous. Okay? Yeah. All right, so that's question number 5. Yeah. Any question? Yeah. I hope you can handle math like this. Yeah. Although we do not have many situations like that. Yeah, it's a relatively hard one. Yeah. All right, question number 6. Log base 2, this side, square root of n. A little harder, but not too much harder. Yeah, just a little more extra things you need to deal with. Square root function. Yeah, not integer. Yeah. This time the exponent number, not integer. It's a fraction. Yeah. We can still, we do the similar way, L'Hopital's rule. Yeah. Replace it by a continuous function, x. All right. We know it is an indeterminate form, so we can apply the L'Hopital's rule, taking derivatives. This time, carefully apply the derivative formulas. Log base 2, yeah. Before we take derivatives, we write square root of x as x to the 1/2 that power. Exponent, yeah, that, power function standard way. Yeah, the power function standard way. Okay, yeah. After that, then I apply the L'Hopital's rule, taking derivatives, yeah. Apply the formula, yeah. Standard formula. This time our a becomes 2. Yeah. So we use our a formula, but replace a by 2. Yeah. A formula replace a by 2. Yeah. I mean log. Okay, log. Yeah, log. Yeah, not the exponent. Log. Yeah, not here. Yeah. Previous. Yeah. Example. Yeah. So we have that. Power rule. Power rule applied to x to the 1/2. That's power function. Bring down the exponent number 1/2 here, and the new exponent, the old exponent -1, so -1/2. -1/2. All right. Then the whole thing, let us do simplification. Yeah. Simplify that ratio, so we get this expression. All right, at this point, after you get this expression, this new ratio, do not apply L'Hopital's rule anymore. All right, at this point, be careful. Do not apply L'Hopital's rule anymore. Why? We cannot apply L'Hopital's rule another time here. Look at numerator. What's that? Constant 2. It's not indeterminate form, right? We require L'Hopital's rule infinity over infinity, 0 over 0, indeterminate form. This 2 numerator determinate. It is determinate, right? Yeah. That's why be careful. Do not apply L'Hopital's rule here. Otherwise, you will get a wrong answer. Yeah. But here, all right, we just consider when x goes to infinity, denominator goes to infinity, so the whole fraction goes to 0. So we get 0. Yeah. Yeah. Probably you can argue, some students may argue, if I apply derivative, I also get 0. Although the answer is correct, but your method is wrong. Yeah. So we need to make sure our method must be correct. Even if the answer is correct, we want to make sure your method is correct. Otherwise, sooner or later, if you use wrong method, sooner or later you will get wrong answer. Okay? Yeah. So you must always make sure your method is correct. Then you can get correct answer. Yeah. So that's example number 6. Yeah. Yeah. All right, so next one. Yeah. So we finish our part of B, so that's, in my PowerPoint slide, I put a B. I need to switch PowerPoint file. Yeah. When I see this symbol, I need to switch PowerPoint file. All right. Start a new PowerPoint file. All right, yeah. More examples. All right, so example number 7. This time we compare natural log function belongs to little o of n to the dth power function, but what is that d number? D we only require d is a positive constant, d greater than 0. That's the only condition we have. Now, let us apply the L'Hopital's rule another time. Yeah. Natural log of x over x to the dth power function. Yeah. Indeterminate form. So we can apply the derivatives immediately. Natural log derivative 1 over x. Okay, yeah. Power rule d times x to the d minus 1 power. Yeah. After simplification, yeah, do simplification. Yeah. So we get 1 over d times x to the dth power. But this time, this new fraction is not indeterminate form. 1, determinate, right? 1. So you cannot apply L'Hopital's rule another time. All right. So let us just consider when x goes to infinity. D positive number. When x goes to infinity, even d is positive. We know x to the d must be infinity. 1 over infinity, 0. So then conclusion, little o. little o. Yeah. So this example is very important. Why very important? Why very important? Here, let me show you the meaning. Natural log function, power function. When we compare log function and a power function, our power function, the d number, we only require it is positive. So that means d could be a very small number. Still positive, right? Think about it. Yeah. So let me write something here. Yeah, let me change the color. All right. Think about, how about d equals, yeah, here, just one special example, d equals 0.000001. Many zeros, how about that? That is a very small positive number. You can see 1/millionth, right? D equals 1/millionth. You take the root function, 1/millionth root. 1/millionth root, how small it is. Yeah? But it is still increases much faster than natural log function. Okay? Even you take 1/millionth root, you get, because when you consider the limit, still the limit equals 0. Okay? But if usually students, based on their intuition, I compare these two functions. I ask them which one increases faster. Okay? Yeah, I give many similar questions in the homework assignment. When they see 1/millionth, 0. so many zero, usually they tell me close to 50%. Close to 50%, they tell me natural log of n increases faster. Natural log of n increases faster. 50% of the chance. Answer is n to the d increases faster. Eventually, think about, we only look at n very large, all right? We don't worry about where n is relatively small. We only look at very large. And one student even argued in this way. It looks pretty convincing, but it's wrong. One student told me he tried to use some online calculator, do calculation, because your little app calculator, you cannot handle that big calculation, right? N to the 0. that power. I don't know if you can handle. So that student used the online calculator, very powerful calculator, like Wolfram Alpha, okay? Wolfram Alpha. Yeah, I use that a lot. Yeah. So they told me when they plug in n numbers, even n numbers really large, that number very, very small. Okay? So they told me log of n is faster. No. Even you plug in numbers using some calculator, the number, the size of the number you can handle very limited, right? Very limited. Yeah. But here we talk about theoretical result. We talk about theoretical result. There is no limitation on the size of the number. No limitation. The number you plug in, you have a limitation because you cannot go too large. You have limitation. But here, our n, no limitation. So that's why our formula, our computation tells us which one is faster. Not based on your experiments, right? Your experiments, you have limitation. So that's why it may not be correct, right? Yeah. So we, based on the math calculation, all right? Yeah. So that's some comments for this question. Yeah. Next, question number 8. Yeah. This one, much harder one. Much harder. N factorial. How can you handle N factorial, right? So this is the most difficult one in this section. Yeah. N factorial. Yeah. Here we say N factorial belongs to little of this special function, n to the nth special exponential function. Very big, very big. N factorial, when we compare these two functions, little o, the limit of n factorial over n to the nth, the limit should be 0, but the question here, the hard part of the question, limit. N factorial, how can you take the limit of the function like this? Even you replace by continuous variable, for continuous variable, what's the meaning of x factorial? Right? The definition is not that clear, although there is a definition. Later we will see there is some generalization of n factorial. But we won't go that way. Even you have the definition x factorial, how to take the derivative. Nobody can tell you what is the derivative of that. So that's why the derivative way is extremely hard. We cannot use the L'Hopital's rule here. So when you see n factorial, don't try to use the L'Hopital's rule. No way you can do it. Nobody can do it. So you have to choose a different way when you see n factorial. Okay? Here we use another formula from calculus. From calculus 2. There is another famous formula related to n factorial. That is the Stirling's formula. Stirling's formula give us estimate for n factorial. Okay. So what is that estimate? Here, n factorial approximately equal to square root of 2 times pi, strange, pi times n, then outside parenthesis, n over e, natural log base, e, all right? N over e, the whole thing raised to nth power. That's the Stirling formula, right? Yeah, we need to use this estimate, Stirling formula. Otherwise, we cannot handle n factorial. But when you use the Stirling formula, here, another thing is not very friendly for us. Look at this approximation sign. Approximately equal, we have problem with that. Because when we want to do some serious math work, that approximate does not provide us precise information. So we have problem with that. Approximately equal, we have that. So we have to change a different version of Stirling formula. Stirling formula has another version we need to use. That is the inequality version, not the approximation version. Inequality, we need that. We need upper bound, lower bound, inequality version. So let us take the inequality version of the Stirling formula. That is the inequality version of Stirling. Lower bound, root of 2 pi n, the same as that, okay, the lower bound. But upper bound, that root of 2 pi, we change that to constant e. Natural log base, constant e. See, 2 pi root lower bound constant, upper bound constant just e. Remaining the same. That's more friendly. This inequality formula, Stirling formula, more friendly for us to do the calculation here. All right. So now we can do the remaining calculation. Work starting from this inequality. Okay? This inequality. All right. Next, the work let us do, so start from there. Let us take the ratio of the f function and the g function. F of n factorial, g of n to the n, ratio of the function. If you look at that in this formula. You do the division, each side divided by n to the n. After simplification, you have this inequality. That inequality. All right. Then, next step, we know we need n goes to infinity, and we want to see the limit when n goes to infinity. Yeah. Let's take the limit when n goes to infinity. All right. But when you do that, make sure the little things, be careful, the little things, the original inequality is strictly less than, but when you take the limit, change the strict less than to less and equal, because the limit will include the equal case. Original formula, strictly less than or strictly greater than, non-equal, unequal, right? But when you go to the limit version, make sure you include the equal case. Otherwise, you will lose a special case, equal case. Yeah. So that's typically we do in calculus. Now let us move to the next step. All right. Look at the limit of the leftmost term. Look at the limit of the rightmost term. Can we see the limit immediately? Look at the numerator function, denominator function. Numerator function, denominator. What is that? The numerator function is a power function, right? Exponent 1/2. Denominator function is an exponential function with the base greater than 1. What is the ratio of that? We did, right, before. Think about that. Limit is 0. When you compare a power function and an exponential function grows much faster than power function. So the limit equals 0. Similarly here, the limit goes to 0. The power function over exponential function, the limit goes to 0. Look at the two ends, limit of two ends. Both ends, the limit go to 0, then the limit in the middle can only go to 0. The limit in the middle can only go to 0. Here we use the previous example. N to the d, that d is 1/2. Exponential function, yeah, a equals e, yeah, little o, that means limit equal to 0. Here, these two limits, we just use that result. Okay, all right. Then after that, both sides goes to 0, then there is a theorem called a squeeze theorem or sandwich theorem. Some people call sandwich theorem. Some people call squeeze theorem. You squeeze the limit in the middle from both sides. Both 0, you do the squeeze, the middle part can only be 0 by the squeeze theorem. Or sandwich, yeah, the sandwich in the middle, the meat in the middle, yeah, must be 0. Okay, must be 0. Yeah. So that is the answer. You see? Yeah, yeah. You see? Yeah. This 0, limit 0, tells us little o notation. Okay. All right. So you can see this is the hardest example in this class. Yeah. Hardest example. And from this example, you can see we need a lot of pieces of knowledge, many pieces. Okay? Stirring formula, squeeze theorem, L'Hopital's. Here we do not apply L'Hopital's rule. Yeah, yeah. All right. Yeah. Example number 9. for each of the following functions, because this is a typical question you may have in the homework assignment. So I like to give you, multiple choice question. We want for each one, here it's not multiple choice. Here, it's a, although there are many options, but we need to work one by one. Yeah. All right. A, B, C, D, E, for each function, we want to get the simplest G function to put the F function. A, B, C, D, E options, I give you F function. This function, find the G of N, is the simplest, and put this function in the big theta of G. Yeah, so that's the requirement we need to do. Yeah. All right, B, root, so you can see relatively complex, but we need to find a simplest G function to represent the growth function of a complex function. Yeah. C, yeah, so complicated. You see, yeah, very complicated. Yeah. D, yeah, yeah, and E, yeah, last one. Okay, last one. Yeah. So this is from textbook. So yeah, here I just show you how to do it. Yeah, pretty simple. Yeah, do not get scared. Yeah, pretty simple. Yeah. The first one, we take the dominant term, drop the minor term. Yeah, we know that minus 1, very little, so we can ignore it. Just take n squared, and then raise to 10th power, you get big theta of n to the 20th. Yeah. The first one, very easy. Yeah. Second one, we also take the dominant term. All right, we ignore the minor terms. All right, then we take the square root, and we can drop the constant 10. We just replace it by constant 1, leading constant. We know that's not important. All right, yeah. Then n squared take root, square root, big theta of n. As our G function, very simple. Okay, yeah. So that's the second example. Yeah. All right. E, yeah. E, because it's simple, so I jump to E faster. Floor function, we know the floor function, the difference with the original function, just less than 1. That term too little, so we can ignore that. Okay. That means you can remove that floor function to make it look simpler. Yeah. Yeah. The difference is very small, so we don't worry about that difference. Okay, yeah. Log base 2, yeah, that base, yeah, here. In computer science, LG, by default, we mean the base is 2. Okay, yeah. LG. In math, that probably base 10. Yeah. In our computer science, we always mean this log base 2. Yeah. All right. This one, 2 exponential terms, one smaller one, one larger one. When we determine the order of growth, we take the larger exponential term. Yeah, so we don't worry about that. Comparing 2 to the n plus 1 and 3 to the n minus 1, the base 3 term dominates base 2 term quickly, dominates. So we just take the dominant term, all right? So then, because minus 1, that's little, we can ignore it. Little number, not important, so that we simplify it, big theta of 3 to the nth. Yeah. And the last one, the hardest one, yeah, looks pretty complicated. Yeah. So we need to see which term is dominant. One dominates the other. So we take the dominant one and throw away the other term. Which one you feel, when n is very large, that one should be bigger. Can you see it? First one or second one? Larger. When n is very large. Okay? Yeah? Let me tell you the answer. Second one dominates the first one. Why? Why? All right. Look at, so here, product of power function, and a log function. Yeah. Each term is a product of a power function and a log function. Constant, not important. Constant, we know, not important. All right. The power function side, n to the first, that power, n squared. This two can be ignored. So n squared dominates n. All right. How about the log side? Log, that 2, we can bring down as 2 times log n plus 2. Yeah? Because log, we have that property. I don't know if I write it. Yeah. Log parenthesis n plus 1 to the square, we have the property, we put a 2 here, 2 times log function n plus 2. We know this kind of constant not important. So basically we compare the log function and that log function divided by 2 by the log property, just minus 1. We know minus 1 not important, right? Too small. So you have log function here, we ignore constant 2, log function. These two log apart comparable. The log apart basically same order of growth. Same, what I mean, not same value, same order of growth. Okay? Log side, same order of growth. But the power function, the second term, higher than the first term. Yeah. So that's why we take the second dominant term, but we want to simplify as much as we can. So the power function, we use n squared. The log side, we drop the division by 2, log of n. Yeah. So that is the best description of that relatively complex function. Yeah. So with these 9 examples, so I try to cover all the common cases. All the common cases we need to see in this class. Yeah. That should be enough. Yeah. So you just study these 9 examples, pretty much cover all the questions you will see in this class. Yeah. When you see a new question, if you cannot answer quickly, you can go back to look at these 9 examples and see which one can give you some related information for your solution. Okay, all right. Yeah. In our first homework assignment, you will see many questions that we discussed today. Yeah, many questions in today's class. Okay, all right. Yeah. And here I want to mention there is a change of base rule for logarithm. Later we may need to use it because here we use log base 2. Later when we change to a different base, we use this change of base rule like this. Yeah. Yeah. Here. Yeah. Here I just mentioned it. Later when we need to use it, I will bring it back. Yeah. Here we may not use it directly. Yeah. Here the reason I talk about this change of base, because in that way you do not need to worry about which base use when we select the g function. Any base pretty much similar. Okay? So you don't worry about the base number because we have this change of base rule here. That's the reason I bring it here. Yeah. But later we have some relatively tricky questions. We need to apply this formula. Change of base formula. If you do not know this formula, those questions could be hard. Yeah. Could be hard. Yeah. Yeah. I will talk about that when we have that question. Yeah. All right. Next, brute force method. Here, I just do some introduction, yeah, because we only have 10 minutes left. Let me give you some introduction. So then we do the real work next time, Wednesday. Wednesday, first we finish remaining slides. We have brute force method topic, remaining slides. Then we start Module 3, recursive algorithms. Module 3, a big module, very important module. Module 3, yeah, on Wednesday. Yeah. Here, let me just do 10-minute introduction for the brute force method. Yeah. First, from its name, you can see brute force. Brute force. From this name, you can see what the typical method looks like. The typical method, brute force, from the literal meaning here, you do not apply any technique. If you apply some special technique, we cannot call brute force, right? Yeah. Brute force typically no special technique. You just work on it in a straightforward way. Straightforward. Okay? Yeah. The thing, you know, the steps you do, just plain, yeah, no technique. Plain steps. Simple, straightforward steps. Yeah. Why I want to talk about brute force method? Yeah. There are several reasons. Yeah. First, when we work on a problem, many times it could be a hard problem. The problem could be very hard. When we have a hard problem, we don't know how to solve it. We don't know how to solve it. So we want to try it. We want to get started first. We need to do some experiments, get started first. But we do not have any idea. In that situation, people here, I mean problem solvers, the problem solver usually try the brute force method first. Because no special technique needed, right? Just to work it out in a simple, straightforward way, because everybody can do that, right? Brute force, everybody can do that. We know it's bad, but we want to work it through first. We want to have a slow method to solve the problem first. Yeah, so that's the reason. It has some value because it is used as the starting point for our typical solution. We're not satisfied with the solution, but we want to get started first. Yeah. So that's the reason people still, although there are many advanced techniques, but people still get started with the brute force method. Yeah. All right, so that's the description of the brute force method. Yeah. All right. Properties of brute force method. Yeah. Yeah. It's a straightforward approach. Yeah. You just use the simplest way everybody knows. Yeah. No special techniques, no special advanced concepts. Okay? No advanced data structures. Yeah? Do not use advanced data structures. If you use advanced data structures, we cannot call it brute force method. Right? Unusual, yeah, brute force, everybody can understand immediately, with our algorithm background. Yeah, I do not say, everybody on the street, with our background, right? Yeah. You can always apply it to a problem. Yeah. It's bad, but you can apply it. Okay? You can, mess with it first. Yeah. All right. In general, it is not the best algorithm. Yeah. In general. But there is a possibility the brute force could give you the best solution. There is a possibility, but that kind of problem usually not hard. Think about that. The brute force method can give you best solution. How can you say it is a hard problem, right? You cannot, right? So in general, it is not the best algorithm. Yeah. It is usually used as the starting point for more advanced algorithms. Yeah. We need to build up our experience when we solve a relatively hard problem. How do you get some experience? Yeah. The first step, you can try brute force method. Yeah. Just get something. Yeah. Then we do the improvement after that. Yeah. We know that won't be our final solution. Won't be. Okay? But we need to try to get some properties of the problem. We want to discover the properties of the problem. And it takes time to do that discovery. Discover the properties of a problem, not easy. It's based on the insight. Can you find the insight of the problem? It's not easy. But before you have the insight, before you find any main properties of the problem, the only way you can work, brute force method. Brute force. You do not rely on any special properties. You do not rely on the insight. You just work it out in a straightforward method. We know it is extremely fast. Extremely fast. Yeah. All right. That's our understanding of the brute force method. The introduction part. Yeah. Next, on Wednesday, we pass the introduction part. We will use the brute force method to solve sorting algorithm. Sorting. Yeah. Sorting. Yeah. Sorting. Yeah. Yeah. I would say that method is close to brute force. Yeah. Because people can argue you use some special concept, you use some special, technique, right? People can argue. Yeah, but if the concept and the technique very simple, too simple, then so we do not treat it as some advanced technique, right? Some advanced concept. We do not treat it as that. Yeah. So we still treat that method very close, at least we can call close to brute force method. Okay, very close to the brute force method. Yeah. All right, so let me stop here for today.